Namaste to all JVN students. Myself, Dr. Priya Gotwal, Faculty of FEM in Department of Chemistry. Today, I'm going to discuss a nomenclature system of the common names of the alkanes. In this, some organic compounds are identified using common names that do not follow the IUPAC system of the nomenclature. Many of these names were given long ago before the IUPAC system was adopted and are still widely used. Additionally, some names are descriptive of shape and structure, like those below. For example, common names for some polycyclic alkanes, which is cubane, which is a cubic-like structure. Hausen, it is a house-like structure. To get the name Hausen, Churchen, which is a church-like structure. The common name is revealed as Churchen, and the Basketane. It is also a hydrocarbon which is known as alkanes. It is like a look like a basket, so get the name after it, Basketane. So the look like structures and the shape, descriptive properties to show its the name is show as a alkane which look like the other objects. The reveal cubicane, which is known as the structure is look like a cube. And now the physical properties of alkanes. Some physical properties of alkanes are given below. Some physical properties like boiling point. Observations, we can see alkanes have low boiling points compared to more polar compounds of comparable size. Here we can say through the examples, propane, acetaldehyde, ethanol, which is the corresponding compounds of the alkanes, which is known as the derivative of the alkanes. Here we see the melting point by low boiling points, negatively charged, minus 40 degrees centigrade, and the molecular weight of the 44. The acetaldehyde, the molecular weight of 44, boiling point is 21 degrees centigrade, and the ethanol, the molecular weight of the 46, and the boiling point is the 79 degree centigrade. As it says, resulting the increasing strength of the intermolecular forces, increasing the boiling points. And the boiling point increases as the number of carbon increases because of increased surface areas. Like that, the CH3, CH2, CH2, CH3, which is known as butane, the boiling point is 0 degree centigrade. Here we can say CH3, CH2, 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 CH3, which is known as pentane, and the boiling point is 36 degrees centigrade. Here we can the countable alkane is 1, 2, 3, 4, 5, and 6. 6 carbon atom containing hydrocarbon is known as hexane, which is also called n-hexane, having a boiling point 69 degree centigrade. So we see here the boiling point increases as the number of carbon atoms increase because of increased surface area. So resulting the increasing surface area, the increasing the boiling point. Next category of the boiling point is the boiling point of isomers. We explain this. The boiling point of isomers decreases with branching because of decreased surface area. So we can see here the neopentane having a boiling point of 10 degrees centigrade, isopentane having a boiling point of 30 degrees centigrade, and the N-pentane having the boiling point of 36 degree centigrade. As we see, that the increasing surface area increasing the boiling point. So this phenomena is affected to the boiling point. And the next property is a solubility. Alkanes are soluble in organic solvents only because these are the non-polar compounds. So alkanes are insoluble in the water. Here the keywords using the boiling point, BP is denoted to boiling point, MP denoted to melting point, VWW is a van der Waals forces, DD is a dipole-dipole interactions, and HP is a hydrogen bonding. So these are some physical properties of the alkanes. Now we discuss about the conformations of the acyclic alkanes. The conformations are different arrangement of atoms that are converted by rotation about a single bond. Carbon-carbon single bond give a rotation through the resulting mixture is known as a conformation, having a different type of arrangements of atoms and groups in a 3D state. So if the rotation occur from here, the rotation generated and two different conformations occurred. The location of the indicated atoms change with the rotation through the conformational isomers, conformational analysis. The conformations are different arrangement of atoms that are interconverted by rotation about single bond. So this is a definition of the conformational analysis of the compound. We can discuss in the next slide. So the names are given to two different conformations. In the eclipsed conformation, the CH on the carbon are directly assigned with the carbon hydrogen single bond on the adjacent carbon. In the staggered conformations, the CH bonds on the one carbon bisect the HCH single bond angle on the adjacent carbon. These two phenomena we can see here. In eclipsed conformations, the CH bond are all aligned. Rotation through the 60-degree and rotation along the carbon-carbon single bond, the staggered conformation occurs. The CH bond in front bisect the HCH bond angle in a back. So here we can the conformational analysis of the alkanes. Rotating the atoms on one carbon by 60-degree converts an eclipsed conformation into a staggered conformation and vice versa. So we can say the angle that separates a bond on one atom from a bond on an adjacent atom is called a dihedral angle. For ethane, in the staggered conformation, the dihedral angle for the CH bond is 60 degree. For eclipse ethane, it is a 0 degrees. Okay, so and on view, looking directly down the carbon-carbon bond. Here we can see the eclipse conformations in front of carbon. This is the back carbon. This is the dihedral angle is a 0. About 60-degree rotation, the eclipse conformation is changed into the staggered conformation. So we can see the carbon-carbon nearby to the 60-degree dihedral angle. This is known as a staggered conformation. And on representation for conformations are commonly drawn using a convention called a Newman projection. How to draw a Newman projection? The problem is occur when we draw a Newman projection. So we follow some steps for using some directions through the Newman projections. Step 1 is looking forward to the look directly towards the down the carbon-carbon bond and on and draw a circle with a dot in the center to represent the carbon of the carbon-carbon single bond. Here we can say the staggered form of the carbon. Here carbon in back and carbon in front. Next, step 2. Draw in bonds. The next step is a draw in bonds in the Newman projection formula of the alkanes. Draw the bonds on the front carbon as three lines meeting at the center of the circle. Draw the bonds on the back carbon as three lines coming out from the edge of the circle. Likewise, the bond in front and the bonds in the back. These three lines show the bonds in the back, and the three lines show the bonds in a front position of the alkane in the Newman projection formula. Step third, add the atoms in each bond. Likewise, these hydrogen atoms are visible in this Newman projection formula. Each carbon atom has 3 hydrogens in ethane. Okay, so this is a Newman projection formula. How can we write? How can we use? So in figure, Newman projection for in the staggered and eclipsed conformations of the ethane, we can see the staggered conformation, the dihedral angle of the ethane is a 60 degree, and the eclipsed conformation, the dihedral angle of the 0 degree between them. In Newman projection formula, the staggered and eclipsed conformation of the propane, here propane considered rotation at one carbon-carbon single bond, which is known as a carbon-carbon sigma bond. Here we can see the 3 hydrogens bonded to this carbon and second hydrogen and 1 CH3 bonded to this carbon. So the staggered conformation of is likely to be held CH3 group in its above the position of the dihedral angle, and eclipsed the conformation, the hydrogen and CH3 are eclipsed and the dihedral angle is a 0. So the staggered and eclipsed conformation of ethane interconvert at room temperature. Yes, it is a very important thing that these two possible phenomena occurs only at the room temperature, but each conformer is not equally stable, right? The staggered conformations are more stable, lower in energy than the eclipsed conformation due to free from the angle strain. Electron repulsion between bonds in the eclipsed conformations increases its energy compared with the staggered conformations, where the bonding electrons are further apart. I say you before, that is the free from its angle strain. Here we see the staggered conformation. The side view of this compound is these CH bonds are the further apart, which is the more stable. Okay, and in this eclipsed conformation, the side view of the compound, these carbon hydrogen bonds are closer together, which is the less stable. So the difference in energy between staggered and eclipsed conformations is nearby 3 kilocalorie per mole, each eclipsed carbon hydrogen bond contributing 1 kilocalorie per mole. The energy difference between staggered and eclipsed conformers is called torsional energy, which is known as torsional energy. So here I defined the torsional energy in a point of torsional strain is an increase in energy caused by eclipsing interactions. Okay, so the energy of the various dihedral angle for the ethane is shown in this figure. As we say that the energy along the dihedral angle, the graph is showed 0 degree, 60, 120 degree, 180 degree, 240 degree up to the 360 degree. Okay, so this is a energy difference, which is a total of 3 kilocalorie per mole. The eclipsed energy is a maximum. We can see by this graph, and the staggered energy is minimum, which is pointed at a lower state. So each HH eclipsing interactions contributes 1 kilocalorie per mole of destabilization of the eclipsed conformations. At any given point, all ethane molecules do not exist in the more stable staggered conformation. Rather, a higher percentage of molecules is present in more stable staggered conformation than any other possible arrangement. So we can say the staggered conformation has a lower energy, minimum energy, and eclipse has a higher energy, which is known as maximum energy. So we can discuss by the energy minimum and maximum occur every 60 degrees as the conformations change from staggered to eclipse. So we know that conformations that are neither staggered nor eclipsed are intermediate in energy. Got it? Okay. The another case of this kind of Newman projections is a butane. Butane and higher molecular weight alkanes have several carbon-carbon bonds, all capable of rotations. It takes 60-degree rotation to turn to the original conformation. Here we can see in figure 6 different conformations of the butane, like the staggered, which is the anti, rotation about 60 degrees centigrade. It is converted to eclipsed, which is also rotated by the 60 degree. The position of the methyl group is in front, which is a staggered, and it is known as Gauchy, which is known as a Gauchy form, because the one CS3, one methyl group is farther away from the methyl, which is the Gauchy. Next, again rotation about the 60 degree, the methyl group is eclipsed to the each other, overlap to the each other, which is due to the rotation of the 60 degree having a dihedral angle of this 0 degree centigrade. And the rotation about also from the eclipsed form is changed or converted into a staggered and Gauchy form. This is, and the final further rotation about the 60 degree, the staggered and Gauchy form is converted into the purely eclipsed form. These are the Newman projection formula of the butane. So a staggered conformation with two or larger groups 180 degree from each other is called NT. Okay, again a staggered conformation with two larger groups 180-degree group from each other is called NT. A staggered conformation with two larger groups 60-degree from each other is called Gauchy. Got it? So the staggered conformations are lower in energy than the eclipsed conformation. The relative energies of the individual staggered conformations depend on the steric strain. Okay, the steric strain is an increase in energy resulting when atoms are forced too close to one another. So Gaussian conformations are generally higher in energy than anti-conformations because of steric strain. So this is due to the steric hindrance occurs, steric phenomena occurs in this kind of examples. Here we can see the anti-conformations, Gaussian conformations, steric strain. Okay, so first I discuss the anti-conformations. The two methyl groups are 180-degree apart, which is known as anti-conformation, which is the lower in the energy. The Gaussian conformation, it has higher in energy due to the two methyl groups are only 60-degree apart. So the steric strain is occur. And the third phenomena, the steric strain caused by two eclipsed CH3 groups. The side view of this product is getting here. So we can see the energy versus dihedral angle for butane. The dihedral angle between two methyl groups are as this. So the staggered conformations 1, 3 and 5 are at energy minima. 1, 3 and 5 are at energy minima, having a lower energy from the others. Anti-conformation first is lower in energy, then the Cauchy conformations 3 and 5 which possess steric strain. Okay, 3 and 5. This possesses steric strain. This is known as a Cauchy conformation. Okay, the eclipsed conformations 2, 4 and 6. The steric 2, 4 and 6 are at maximum of energy due to the two eclipsed CS3 groups in a highest in the energy. So this is the energy level diagram of the butane. So in this table, we summarize the torsional and steric strain energies in acyclic alkanes like ethane, methane, propane, butane, hexane, etc. So, sorry, the type of interaction, and energy increases kilocalorie per mole. Here, HH eclipsing, the energy is 1 kilocalorie per mole. For H and CH3 eclipsing, the 1.5 kilocalorie per mole. CH3 eclipsing, the 4 kilocalorie per mole, and the Cauchy CH3 groups, the 0.9 energy, 0.9 kilocalorie per mole is occurred. So we can say that the methyl eclipsing is a higher energy of the Cauchy, higher energy of the Newman projection formula. So the difference, energy difference between the lowest and highest energy conformation is called barrier to rotation, which is known as barrier to rotation. Since the lowest energy conformation has all bonds staggered and all large groups anti-alkanes are often drawn in zigzag skeleton structure to indicate this. So in this, the zigzag arrangement keeps all carbons staggered and the anti. We can see here this phenomena is occurred during this course of the reaction. So we can see this carbon is a wedge and dashed structure. This is known as a staggered anti-conformation of the alkanes. So like the introduction to the cycloalkanes, further, beside torsional strain and steric strain, the conformations of cycloalkanes are also affected by the angle strain. So angle strain is an increase in the bond energy when bond angles deviated from optimum tetrahedral angle of 109.5 degree. So the Baer strain theory was formulated when it was thought that the rings were flat. It states that larger rings would be a very highly strained as their bond angles would be very different from the optimum 109.5 degree. So it turns out that cycloalkanes with more than 3 carbon atoms in the ring are not flat molecules. They are puckered to reduce strain. So in this video, we can see the small internal angles, which is known as angle strain in 60 degree. Here is a 90 degree, and the larger internal angles, which is known as angle strain, which is a 144 degree. So three-dimensional structure of some cycloalkanes is shown here. In cyclohexane case, now we discuss a cyclohexane. The angle strain. If a cyclohexane ring were flat, then the angle strain is 120 degree. The internal bond angle is greater than the 109.5 degree. Here, the torsional strain is also occur during this conformation. The all hydrogens are aligned, which is known as a torsional strain. In reality, cyclohexane adopts a puckered chaired conformations, which is more stable than any other possible conformations. The carbon skeleton of chair cyclohexane in the chair conformation is so stable because it eliminates angle of strain. All carbon angles are in 109.5 degree, and the torsional strain, all hydrogens on adjacent carbon atoms are staggered. So we can see all hydrogens are staggered in this chair conformation. We can see here this type of strain. And the additional one more example of this, the 3D dimensional model of the chair conformation of the cyclohexane with all hydrogen atoms is drawn below. Here the axial hydrogens are labeled in blue. We can see like this. And the equatorial hydrogens are labeled in gray. Here we can see. That is the difference between this. Okay. In cyclohexane, three carbon atoms puckered up and the three carbon atoms puckered down, alternating around the ring. Each carbon in cyclohexane has two different kinds of hydrogens. First, axial hydrogen are located above and below the ring or along the perpendicular axis. Second is equatorial hydrogens are located in the plane of the ring around the equator. Okay, so here we can see three up carbons and three down carbons. Two kinds of hydrogens are axial and equatorial. Axial bonds are oriented above and below. Equatorial bonds are oriented around the equator. Okay, so we can discuss, draw some problems are occurred during the course of the study of the cyclohexanes. Likewise, some of the problems, draw the chair form of cyclohexanes. Okay, so step first, draw the carbon skeleton. Firstly, draw three parts of the chairs, a wedge, a set of parallel lines, another wedge. Then join them together. The bottom three carbons come out of the page, and for this reason, bonds to them are often highlighted in bold. Second step is labeled the ups carbons and downs carbons on the ring, likewise. And step 3, draw in axial hydrogen atoms. 3 axial hydrogens above the ring and the 3 axial hydrogens below the ring. Okay. Here are some examples. So an important thing is, important conformation change in cyclohexane involves the ring flipping. Ring flipping is a two-step process. As a result of a ring flip, the up carbon becomes down carbon and the down carbon becomes up carbon, which is known as flipping of the atoms, flipping of the carbon in a molecule. The axial and equatorial hydrogen atoms are also interconverted during the ring flip. Axial hydrogen becomes equatorial hydrogen and equatorial hydrogen becomes axial hydrogen. Got it? We can see in this example. The chair form, it is a down carbon flips up, a bot form, and up. Carbon flip down. Second is a chair form. We can see the bond conformation of the cyclohexane. So the chair form of cyclohexanes, the chair form of cyclohexanes are 7 kilocalorie per mole more stable than the bond forms, and the bond conformation is destabilized by the torsional strain because the hydrogen on the 4 carbon atoms in the plane are eclipsed. Additionally, there is a steric strain because two hydrogen at either end of the bond and the flagpole hydrogens are forced close to each other. So we can see the two views of the bond conformation of the cyclohexane. Eclipsed hydrogen are here in a gray and the eclipsed hydrogen in, and the flagpole hydrogen is see here. So the both form of cyclohexane is less stable than the chair form for two reasons. Eclipsing interaction between hydrogens cause torsional strain. And the second thing is the proximity of the flagpole hydrogens cause steric strain. So this is the conformational study of the cyclohexane. So the next, so I till so next video I will discuss in the another topic. Thank you.